everybody. Today I'm going to talk about face alignment across large poses, a 3D solution. My name is Mohammed Shia, and here we go. Um, Traditional face alignments aims to locate visual points like eye corner, nose tip, and chin center based on which face image can be normalized. It is an essential processing step for many face analysis tasks. Example, face recognition, expression recognition, inverse rendering. The researches in face alignment can be divided into two categories: the analysis by synthesis based and regression based. The former simulates the process of image generation and achieves alignments by minimizing the difference between model appearance and input image. The latter extracts features around key point and regresses it to the ground truth landmark. With the development in the last decade, face alignment across medium poses where the yaw angle is less than 45 degrees and all the landmarks are visible has been well addressed. However, face alignment across large poses at 90-degree angle is still a challenging problem without much attention and achievements. For the paper overview, we have the face alignment, which fits a face model to an image and extracts the semantic meaning of facial pixels, has been an important topic in CV community. However, most algorithms are designed for faces in small to medium poses below 45 degree, lacking the ability to align faces in large poses up to 90 degree. The challenges are threefold. Firstly, the commonly used landmark-based face model assumes that all the landmarks are visible and is therefore not suitable for profile views. Secondly, the face appearance varies more dramatically across large poses, ranging from frontal view to profile view. Thirdly, labeling landmarks in large poses is extremely challenging since the invisible landmark shape to be guessed. For the overview, in this paper, author proposed a solution to the three problems in a new alignment framework called 3D Dense Face Alignment, 3DDFA, in which a dense 3D face model is fitted to the image via convolutional neural network CNN. Author also proposed a method to synthesize large-scale training samples in profile views to solve the third problem of data labeling. Experiments on the challenging AFLW database show that our approach achieves significant improvements over state-of-the-art method. Um, Fitting results of 3DDFA. For each pair of the four results, on the left is the rendering of the fitted 3D shape with the mean texture, which is made transparent to demonstrate the fitting accuracy. On the right is the landmarks overlaid on the 3D face model, in which the blue-red ones indicate visible, invisible landmarks. The visibility is directly computed from the fitted dense model. More results are demonstrated in supplemental material. For the related work, we have generic face alignment. Face alignment in 2D aims at locating a sparse set of fiducial facial landmarks. A number of achievements have been made, including the classic active appearance model AAM, sorry, and constrained local model CLM. Recently, the regression based method, which maps the disc- discriminative features around landmarks to the desired landmark position, has been proposed. By utilizing the feedback characteristics that the output landmark position of the regression has an influence on the input featured at landmarks. The cascaded regression cascades a list of weak regression regressors to reduce the alignment error progressively and reaches the state of the art. Sun ETAL firstly uses CNN to regress landmark locations with the raw face image. Liang, Liang ETAL improves the flexibility by estimating the landmark response map. Zhang ETL further combined face alignment with attribute analysis through multitask CNN to boost the performance of both tasks. Large pose face alignment. Despite the great attentions on face alignment, literature on large pose scenario is rather limited. The most common method is multi-view framework, which uses different landmark configurations for different views. For example, TSPM and CDM employ a DPM-like method to align faces with different shape models, among which the highest possibility is chosen as the final result. However, since every view has to be tested, the computation cost of multi-view method is always high. Besides 2D methods, 3D face alignments, which fits a 3D morphable model 3D by minimizing the difference between image and model appearance, also has the potential to deal with large poses. However, it suffers from the 1 minute per image computation cost. Recently, regression based 3D fitting, which estimates the model parameters by regressing the features at landmark position, has been efficient. 3D dense face alignment. In this section, we introduce the 3D dense face alignment, which fits 3D morphable model with Cascade CNN. 3D DFA overview. Blends ETL proposed the 3D morphable model 3D which describes the 3D face space with PCA. Here we have the formula where S is a 3D face, S is the mean shape, 8 is the principal axis trained on the 3D face scans with neutral expressions, and alpha ID is the shape parameter. A expression is the principal axis trained on the offsets between expression scans and neutral scans, and alpha expression is the expression parameter. In this work, the 8 and the A expression come from BFM and Face Warehouse respectively. Here we have another formula. The 3D face is the projected onto the image plane with weak perspective projection. Here we have VP equals to F star PR star R multiplied by S plus AID alpha ID plus A expression alpha expression plus T 2D, where VP is the model construction and projection function leading to the 2D position of model's vertices. F is the scale factor. PR is the orthographic projection matrix 100,010. R is the rotation matrix constructed from rotation angles, pitch, yaw, roll, and T2D is the translation vector. Experiments. In this section, author evaluates the performance of 3DD FA in three common phase alignment tasks. In the wild example, medium pose phase alignment, large pose phase alignment, and 3D phase alignment. Due to space constraint, qualitative alignment results are shown in supplement material. Datasets. Evaluation are conducted with three databases: 300W, AFLW, and specifically constructed AFLW 2000 3D database. 300W LP, 300W standardized multiple alignments database with 68 landmarks, including AFW, LFPW, Helen, iBug, XM2VTS. With 300, we adopt the proposed phase profiling to generate 61,225 samples across large poses, 1,786 from iBug, 5,207 from AFW, 16,556 from LFPW, and 37,676 from Helen. XM2 VTS is not used, which is further expanded to 122,450 samples with flipping. Author call the database as the 300W across large poses, 300W LP. AFLW contains 21,080 in the wild phases, with large poses variations, yaw from 90 to minus 90 to 90 degree. Each image is annotated with up to 21 visible landmarks. The data set is very suitable for evaluating phase alignment performance across large poses. Performance analysis, error reduction in Cascade. To analyze the error reduction process in Cascade and evaluate the effect of initialization regeneration, author divides 300W LP into 97,967 samples for training and 24,483 samples for testing without identity overlapping. Next slide figure shows the training and testing errors at each iteration with and without initialization regeneration. Performance analysis. Here are the tables A and B. Performance analysis. During testing, 3DDFA takes 25.24 ms for each iteration, 17.49 ms for PNCC. Construction on 3.40 GHz CPU and 7.75 ms for CNN on GTX Titan Black GPU. Note that the computing time of PNCC can be greatly reduced if Z buffer is conducted on GPU. Considering both effectiveness and efficiency, we chose 3 iterations in 3D DFA. Performance with different costs. In this experiment, author demonstrates the performance with different costs, including PDC, VDC, and WPDC. Previous figure demonstrates the testing errors at each iteration. All the networks are trained until coherence. It is shown that PDC cannot well model the fitting error, converts to an unsatisfied result. VDC is better than PDC, but the pathological curvature problem makes it only con- uh, concentrate on a small set of parameters, which limits its performance. WPDC explicitly models the priority of each parameter and adaptively optimizes them with the parameter weights, leading to the best result. Here, performance with different costs. In conclusion, in this paper, author proposes a novel method, 3D dense face alignment, which well solves the problem of face alignments across large poses. Different from traditional methods, 3D DFA skips to the 2D landmarks detection and starts from 3D MM fitting with Cascade CNN to handle the self-occlusion problem. A face profiling algorithm is also proposed to synthesize face appearance in profile view, providing abundant samples for training. Experiments show the state of the art performance in AFLW 2003T, and 300W. Thank you very much.